this first one is pretty straightforward. Again, we have a balance of torque problem. So here we're assuming the sticks have no mass and the numbers on top are just telling us the ratio between their lengths. So here, if I have a mass of 5 pulling down here, 5, this torque and this torque, this is my pivot point, those torques have to equal each other. So here I'm saying basically 5 times 3 has to equal 4 times x. And so the x is going to be what this mass is right here. So 5 times 3 is clearly 15. 15 divided by 4 gives me a nice 3.75. Now the 3.75 and the 5 together make 8.75. So 8.75 in total is pulling down on that string. That's not an answer though, so we're not putting a box around it. So we have the 8.75, and now if we jump up to the next one, again, this torque going this way has to equal this torque this way. Well, the 8.75 is times 5, and then we're dividing by the 2 on the other side. So this one here must be a total of 21.875. So then the 21.875 plus the 8.75 means that the total going on this string up here is 30.625. So that string is pulling down against a 6 distance, and then it has to bounce out a 5 distance, so this distance over here has to be bigger. If the distance is smaller, the force is bigger. So again, that 30 times the 6 divided by the 5 means that the total over here is going to be 36.75. And so if I add that 36.75 to the 30.625, that means my total up here is going to be 67.375. That's not an answer I'm going to ask you for, but this is going to be something we can use to check at the end. So it's good to know. So then when we're going down, we have to look at it a little bit different than we did when we were moving our way up. So now we look at this and we say, well, this stick right here has a total length of 4, and one of it is over here to the right. So if we have only 1/4 to the right, then we need 3/4 of the mass over here. And on the left side, since we have 3 times the distance, we need only 1/4 of the mass over there. So if we take that 36.75 and we divide it by 4 times 3, it's going to give me this mass here of 27.5625 kilograms. And then of course, if we just flip that to the other side, this string here will be 9.1875. So that's going to be the total pulling down on that string. So again, the ratio still works out the same. You still have 27.5 times 1 divided by 3 still gives us the 9.1875. So that ratio that we were working with before still works. Now down here it's the same thing. This torque over here has to balance out this torque. So since the left side is a smaller distance, we'll have a bigger force on the left. The right side is a bigger force, so it'll have the smaller mass. But again, we look at this out of that 9, we have a total of 5 here. So on the bigger side, on the 3 side, basically 2/5 of it need to go over here because the smaller mass needs to go with the bigger distance, and then 3/5 of it need to go on the side with the smaller force. So if I'm going to take that 9.1875 and multiply times 2 divided by 5, that tells me that here I'm going to have 3.675 is pulling on this side, and then again I can take the 9.1875 times 3/5, or I can just say times 3 divided by 2 if I prefer it that way. And over here I'm going to get the 5.5125. Now, if we look at all the boxes that are on the bottom, all the boxes that actually represent one of the circles, and we add them up, it should come up to our check number at the top. So if we take that 5.5125 and we add the 3.675 and we add 27.5625 boxes, and that gets me to 67.375, which, hey, that was my check number at the top. So that means I didn't screw up anywhere, because otherwise my masses would not equal like that. So that's all you gotta do for that one. It's not too bad. You don't have to carry out to that absurd decimals like I did. I just didn't round anything at all here. If you want to round, let's go ahead. You can round it, and then your check number again should be very similar. It will not be quite as exact. But that's it.